afternoon. Today we are into the second lecture of the systems engineering course, and today mostly of our discussions will be about the history of systems engineering. And I am Dr. Deepa Philip again from IIT Kanpur. And today's lecture is kind of important because we need to know how systems engineering evolved as a profession and discipline, so that we can so that we have a clear idea where we will be going in the future. So today's learning agenda is how did the systems engineering originated, and whenever we see this abbreviation called SE, throughout this lecture I will be using SE as an abbreviation for systems engineering. We will also talk about what are the factors that are influencing the modern systems engineering as a discipline, and what are the factors that actually contributed to the evolution of the modern systems engineering. We will also talk about examples of systems needing systems engineering. Also, we will discuss in detail some of the output processes, input, stuff like that. And also have a brief discussion about how does systems engineering work as a profession for the students. So, the students or practitioners who are actually taking this course, you need to know where will you go forward in your career by learning through this course. So, we will try to cover up that as well. So, first we will recap on what systems engineering is of our first lecture. We defined systems in multiple ways, and we talked about how system engineering definitions evolved in the previous lecture. So, summarizing all of that and kind of putting it in our own words, today we will say is that systems is a set of interconnected and interacting things. We use the word things in a broad sense. So, the two major things are interconnection and interactions. Interconnection means the different components or the things of the systems are connected to each other, so that they have to work in unison, and interacting in a sense that the input from one or the output from one thing result becomes the input to the other, which will kind of either sequentially or parallelly trigger certain functions towards realizing the common goal. So, these things all interact and interconnect together to produce its own behavioral pattern. The system will create its own behavioral pattern over time. As the time progresses, as time increases, the system behavior will approach what are the desired aspects of the system. In the things, what we call as the things which is part of the system, we will define that as or to include people. People means it can be trained workers, it can be people who are doing surveys, people who are doing feedback from the customers, people who are working in the field providing the warranty, all sort of people, human resources, let us call it as human resource in a general sense. So, all of the human resources associated with the system is encompassed in the term people. So, we will kind of call it as HR. And hardware includes almost all the machines, circuit boards, tools, all those kind of stuff that is part of the system. Then we also talk about software, which is computer programs that are actually part of the system, which will result in realizing certain automation and stuff like that. We will discuss this later down the slides today. Facilities, it involves the buildings, the machining centers, the assembly places, the quality control facilities, special purpose applications, all those kind of things that are necessary to realize the interaction and interconnections of the things. Policies, which could be operational policies, or it could be other guidelines, so or processing policies. There are many things that could happen as part of this. How the system will work, that kind of a document becomes the policy. And documents which are related to, sometimes it could be stuff like assembly diagrams, sometimes it could be like work study diagrams, time and motion studies, product sequencing, all those kind of things as part of those. So, all these things work in unison together to realize the behavioral pattern of the system over time. So, if you look at it in a little bit more broader sense, systems engineering, if you write it here, systems engineering, it is a methodical and a disciplined approach. The approach is both methodical and as well as disciplined. Methodical means it do have a specific sequence and an order, a method, a process, a script by which you follow the approach of systems engineering. And it is also disciplined in a sense that you actually do it in the way it is described to do it. You just don't do it the way you like to do it, but you do it the way it is supposed to be done. So both methodical and disciplined approach together, both of these put together, we can call it as a systems engineering approach, which works on a system for what? The what aspect is, it can be for designing the system, or we are trying to designing in a sense, specifying the parameters or the characteristics of the system, or what it's going to accomplish as an output. Then realization means converting the design to a prototype or a product which can be deployed or used by a customer to realize a specific capability or fulfill a need. Also the technical management, which means how will you streamline and control the engineering process by which the design gets translated to a usable product. As we said earlier, we are mostly talking in this course about product based systems engineering. We are not spending too much time on the services based systems engineering. So the technical management, we can also think about it as product management or product development management. Then the operations, how is the system works, how does the system gets operated, when the person uses it in the field, how does the system works, or how does the production system works to realize the product. All those kind of things are part of the operations. So it is basically a transformation process where inputs gets translated to an output, and the operations that are required to translate the input to the output comes under this operation stuff. And then finally comes the last part, which is called as the retirement, because every system after a certain point of time, it meets its life cycle. So the retirement is related to the life cycle of the system. And when the product reaches or the system reaches the end of its life cycle, how do you retire the system, or how do you take care of the disposal of the product? That aspect is also the part of the systems engineering. So if you think about it, the phrase from the design to the realization to the technical management to the operations to the retirement, and certain cases it goes back in the what we call as the redesign concept. All of these things comes as part of the systems engineering. This is where the multiple versions of the product happens. So with that, let's talk about the origins of the systems engineering. There are not really clear-cut origins declared or defined that this is the particular day and time which systems engineering evolved as a field. The earliest documentation, many of the systems engineering textbooks and authors and other people do cite this example. This is a biblical example, Noah's Ark. Biblical example where Noah ended up building a big ark, or a big like kind of a ship, which was built to a specification, which was designed to carry male and a female of each every available species in the earth, and so that when the big flood happens, everybody will be saved, kind of a thing. So this Noah's Ark is kind of what people call it as the oldest documented evidence of a systems engineering approach, or where a system was built to a defined specification. But biblical examples aside, most of the people agree, or most of the researchers and practitioners in systems engineering do agree with the fact that the World War II is where the systems engineering, WW2 is the World War II, where systems engineering as a field started getting its recognition. So in 1950s to 1960s, this is a time period where many books, literature, research publications, and all other aspects that are related to systems engineering started to get published, printed, and this is where the knowledge and practices start of systems engineering started to evolve. The scientific knowledge associated, the proper documented knowledge with a scientific approach started developing around this area. But by the way, in that time period, in 1950s and 60s, the initial phases of systems engineering, it was driven by the countries or different nations' greed or their want to gain military superiority. How do we gain military superiority over the adversary. That was the major question that was going on. So a lot of the systems engineering initial development started with military systems, which to a large extent you can think about it as weapons, plus the platforms for weapons. Maybe it can aircraft, it could be a ship, it could be submarine, doesn't matter, or missiles. All of them were originally developed as part of they were the initial products that came out of through the systems engineering process. And most of these systems are complex because there is many aspects involved in it. There are materials, there is payload, there is control, there is feedback, there is corrections. So all those kind of things which require multiple aspects of engineering is involved in the development of these military systems. Hence, the systems engineering initially was confined to a lot in towards doing military development. And plus also in United States, NASA was also a big practitioner of systems engineering. NASA is the space agency, North American Space Agency. So we say that all of the complex systems that are associated with the military was developed through systems engineering. One of the aspects that also drove the systems engineering big time was that at the time of war, you don't have the luxury of time, because if your adversary comes up with a efficient product or a weapon, then your chances of winning the war diminishes significantly. Hence, the time to develop the product was also a big criteria. So once the times were crunched, or what we call it as the time availability, when they were significantly reduced during wartime, so there needed an approach that could actually see the faster or quicker developments of the military systems. So that was also another aspect which forced the development of the systems engineering. And so even though it was mostly confined to the military field, one of the development that actually made systems engineering to come out of the military realm towards a much more of a engineering discipline and start to spread its wings into multiple other products and systems and complicated aspects was the advent of the solid state electronics, or in a simple way to say it is the development or the advancements in the computer technology. As computer technologies advanced, the solid state electronics advanced, computation's power increased, the capabilities that you could do by doing large number of data analysis, number crunching, doing designs using computers like CAD, CAM, all those kind of things, they all facilitated towards rapid design and development of systems, complex systems. So the computers, to a large extent, after the initial World War phase, where the aim of the systems engineering was to design complex military systems to gain military superiority, it translated to design any complex system the most efficient way possible. And the computers actually did facilitate it. Actually made the systems engineering much more accessible to simpler tasks. So the modern systems engineering, after the advent of the computers and the advancements of it, is basically driven by three basic factors: the technological advancements, the global competition, and specialization. We will talk about all these factors and how they actually result in the development of modern systems engineering in the next slides. So the technological advancements, we all know that technology now is developing at a breakneck speed. The main factors of the systems engineering to a large extent is the rapid technological advancements that has happened. In earlier days, when the automated machines, or what we call as the CNC machines, computer numerical control machines, came in, they were considered as the epitome of technological advancements. So now from there we have moved into what we call as a flexible manufacturing systems, where you give kind of the raw materials and the production schedule, and the machines automatically produce those parts and give it back to you, which is like a factory, almost like a no man required factories kind of things. So development, the technological advancements to a large extent drove the beyond the World War developments of the systems engineering, which is in 1970s and 80s. the systems engineering was driven by technological advancements. The technology also extended the capabilities of the system. In a simpler sense, the aircraft systems, they were earlier, transatlantic flights were a big thing. Now flights that circumnavigate the globe is not a big deal. Telecom, when original connections with the telephone wire telephone connections, which actually was developed as AT&T Bell Labs and all, was there, people were like surprised that you could talk to a person who is far away through a telephone. You could hear the voice. It was a big thing. But then with the advent of mobile phones, the telephones, which was landline based telephones, has now become almost an obsolete item. Similarly, power plants, earlier everybody used during the time of the World War, nuclear weapons were used as a destructive tool. But after which the technological advancements figured out that the nuclear energy can be harnessed for better civilian needs like producing clean power, and then nuclear power plants came in, and that was one of the other aspects why the technological advancements resulted in engineering of complicated plants like nuclear power plants using systems engineering. Similarly, manufacturing, earlier aspects of, like for example, automotive manufacturing to a large extent was skilled assembly, hand-built motors. From there, specialized machines, tools, robots, painting mechanisms, all those kind of things has put together, has made almost the development or the manufacturing of an automotive to a large extent heavily automated process. We will see some of the other aspects of this in the later slides. Similarly, technology also have created new systems. First one is it increased the capabilities of the existing systems. Another one is it also created new systems. And most of the new systems that are created, which was in 90s and 2000s, they all have been heavily computer dependent. Like earlier in the land-based telephones, the presence of a chip was not an important thing. There was actually no chips present. Whereas in a mobile phone, you are talking about a processor, the memory. It is almost like a mini computer that you carry around from your in your pocket, in which you can do a lot of your daily activities. Similarly, other system that earlier, when you had to go from a place A to place B, nobody even thought about a system called satellite navigation, or what we popularly call it as GPS based system, global positioning system. Nobody thought that satellites could be used for navigation or help you to go from place A to place B, find your route. Similarly, entertainment. When Edison developed the projection or projector, movie projector, it was considered as a great advancements in entertainment. But with the advent of the digital technology and satellite and other things, the concept of the tape and the movie reels and other things were replaced by digital movie systems. So the concept of the entertainment with the new advancements in sound systems, where you could actually feel you could always people call it as 3D or virtual reality or whatever you want to call it. But entertainment also with advancements of new system has gone much higher. Healthcare, earlier it was X-ray films. Now almost all the healthcare is in a tablet in front of the doctor. By the time you reach his office, he kind of knows your history. So the advancements of the imaging and other aspects of increase the assurity and as well as capabilities of the healthcare systems. In earlier days, finance was mostly dependent upon reliable local branches, and where you have to go to foreign countries, you are expected to carry the foreign currency or something called as traveler's check. With advances in computer systems and as well as the databases and interconnectivity, internet and stuff like that, you could now come up with plastic money, which you could carry like a credit card in your pocket, which you could take it anywhere across the globe and then do the needful. So the new systems development also brought in stuff or also brought in complexities, because most of the time engineering is kind of, in the simplest way you can put it, is you kind of have, the theory and you're trying to put the theory into practice. But when new systems or new technologies are created or innovated, this is the better phrase, innovation, creating better technologies, which kind of results in new stuff beyond the known theory. So when the new stuff is available, which you have a lot of unknowns, or you are not completely sure about the whole theory behind it, then to develop a system out of it, you require checks and balances. That is also one other major aspects of systems engineering. Also, the technological advancements that we talk about, it is not without its own risk as well. We need to know the risk of the technological advancements. One of the major risks that comes from is what happens if you do not embrace technological advancements. So, if no to technology, if that is what company does or an organization does, then they do stand the risk of developing inferior or obsolete systems. Some of the public sector companies in India are good examples of this, where the sluggishness in adopting advanced technologies have resulted in developing obsolete systems. So, an organization, if it needs to be staying ahead of the ahead of the competitors and develop products which the customer wants or the customer needs, then they need to embrace technological advancements as quickly as possible and assimilate those technological advancements into their organization. Also, systems engineering does beautifully incorporate the risk management, concept of risk management into the development of a new system. So, risk, in a simple way to define it, is the chance of acquiring or losing something of value. So, when you talk about acquiring or losing something of value, you could either gain or you could lose. It could be both. Okay. So, if you do not embrace that capability, like an example, it is talked about how IBM as a technological giant refused to get into the personal computer market, where they stayed with the servers and the mainframe systems. So, the IBM focused on mainframes and servers and did not give too much of focus on the personal computers, resulted in the PC market to a large extent dominated by companies like HP, and then there is another one, I am forgetting the name, but Dell, stuff like that. Those are, or Compaq was another example. So, these companies who focused specifically on PC market or personal computer market ended up growing way much better and becoming more profitable than IBM, because in the later run the number of units that were sold in the PC market were way much higher than the mainframe and the server market. So, that is actually the opportunity lost in not being able to tap that market, is the risk that IBM stood by not embracing that technological advancements. Similarly, another advancements we also need to discuss about it is the software advancements. From the simpler languages like Fortran and Pascal, which were mostly text based stuff and where even high-fi or high fidelity user interfaces were of a dream, the development of the better information processing and hardware, both hardware and software, has helped in one of the major things which is called as large scale automation of the control functions. In the earlier days of systems engineering, you could not think about something like a CNC machine. So, you load the workpiece, you put the tool, and then you give a program, computer program, which the machine follows, which decides when to cut, where to cut, what is the depth of the cut, what is the feed rate, how much of the coolant to be used. All these aspects taken care of by the system automatically, not a human being standing there and doing it, so that you could actually optimally produce. That is one thing that was never thought through, but the advance in technological systems, both hardware and software and computer systems, have made CNC machines reality. Now we have much higher versions, higher capabilities of CNC machines. Nobody even thought about what we call as AGVs, automated guided vehicles, which could transport one part from one machine to another. We all thought you require a human being to move from a part from one machine to another, but now AGVs are available. So, this large scale automation has brought in lot more advanced capabilities in the system, but it also brought its own problems. You have a human machine interface and as well as you have people system interface. These interfaces, which were not there in the earlier systems, have now realized because of the advancements in the automation system. So, earlier the skilled worker was supposed to stand in a machine and work, whereas currently a skilled worker is supposed to supervise the machine and see that it is actually doing the executing the program as per the CNC program that is loaded onto the CNC controller. So the new interfaces became another concept of another aspect that systems engineering need to be worried about. Then we talk about the second factor, which is the global competition. So this is the second factor. We were talking about the technological advancements earlier. So obviously the first thing that actually drive development of new products or new technologies or new systems is the pressure from potential adversaries. Classical example is that the country, any country if you take, they have a list of friendly nations and as well as adversary nations, and depends upon what all technology the adversary has. The country try to develop capabilities to combat the technologies or systems that the adversary has. And another example of this is the competitive contracting. When this happened, like when the Indian market was open to the global population, then the public sector companies who enjoyed the license Raj concept had to face a stiff competition and technologically advanced competitions from across the globe, and some of them actually did falter. So the competitive contracting, when you're going for a globalization where much more technological advancement happens across the globe, then this becomes a problem. We also can talk about the first mover advantage. If the competition, if you come into the across the market, when Apple came up with the smartphone, when they incorporated things like capabilities to browse internet, have a camera, a torch light, a music system, everything into a phone, people made fun of it. I mean, who would do this? But pretty soon Apple introduced the concept of smartphones, which to a large extent has changed the world in which the way in which people start using mobile phones. Similarly, cost effective. Everybody knows about the AMD and Intel, who are the largest chip manufacturers in the world. Chip means I'm talking about processors, and how they are cost conscious. So if you're a cost conscious person, you might go with certain processors in AMD. If you're an overclocking person, you might go with AMD. Whereas if you're looking at a number crunching, then you might go with an Intel processor. So depending upon different applications and with the financial considerations in mind, you might choose one product over the other. And also another aspect is when the systems became more complex, more things were added to the system, the requirement of funding, the financial requirements also started going up significantly. So the project which could earlier be done in one go, you have to do it in phases now. So the phasing or making it into parts, logically manageable parts, is another aspect of the systems engineering. Finally, there is a competition between performance, cost and schedule. You would want the system to do everything at the best performance. Also, you want it at the lowest cost, and you also want to develop it within the required time schedule. All these three are conflicting in nature, and it is quite hard to realize all of them. Realize all is hard. So you compromise, and systems engineering allows you to decide when to compromise and what to compromise. And the last part about that we wanted to talk about is specialization. The specialization is to a large extent depends upon as the system complexity increased, the systems are capable of doing multiple functions at the same time or multiple capabilities. Earlier, a mobile phone was supposed to be used for contacting somebody. It was supposed to do the concept of telephoning someone. Now the phone also manages your alarm, it manages your calendar, it manages your email. It started doing the healthcare or remote monitoring your blood pressure, blood sugar, all those kind of stuff. It is now a global positioning system or a mapping or a guidance based systems. So all these capabilities, when you have complex systems with multiple capabilities come in, then a lot of the major functions need to be compartmentalized. Because the requirements of a GPS or a navigation system where GPS is needed, and the requirement of a mobile phone where you're just making a telephone call to someone, are two different things. So both these applications require compartmentalization. So when you have the compartmentalization is usually achieved through something called as modularity. You make things modules for realizing functions. So, when you have modularity, then specialization is realized through modularity. So, in a simplest sense, when you have too much of things which are modular, they all need to be integrated together. So, the systems engineering, when you have modularity, the integration of them, integration of modules becomes another aspects, another factor that drove the development of systems engineering. To a large extent, this interchangeable parts and automated assembly, it required systems engineering. These two things, to a large extent, drove the systems engineering to its current state of expertise. Some of the complex systems, this is kind of our last slide, we'll conclude here. One of the examples of complex system is the aircraft assembly. As I mentioned earlier, aircraft in which you include materials, you have a propulsion system in the form of engine, it can be a turbo propeller or a jet engine, you have a fuel system, you have a control systems, you have a lot of decisions to make, like if it's a passenger aircraft, you want to reduce the weight. So one way to do it is don't put any cushion on the seat, but then the passenger who is sitting on the seat will not be comfortable. So you want to provide some cushion to that. So then people were like, okay, why don't we make the cushion in such a way that it can be also used as a flotation device in the wake of a mishap. So combining functionalities and other kind of things, people started making aircrafts much more lighter so that it could travel much more longer distances. Similarly, air traffic control is you have aircrafts which are landing, taking off, taxiing, parking, maintaining, all those kind of things going on crazy in an airport. So air traffic control do provide a complicated system which gives a bird's eye view of what is happening in the airport. Similarly, the patient information system is another example which I mentioned earlier. Automotive manufacturing, you can actually see how different robots by in itself are manufacturing the automotive. Electric power plant, I mentioned about the nuclear power system, how it was being developed as a system to track to harness the civilian or the clean aspects of nuclear energy. Similarly, satellite systems, how we can see the solar panels, then you can see the payloads coming right here, the communication, all those aspects are part of such complex systems. So as a profession, as systems engineering as a profession, where do you go from here as a systems engineer? One of the things I suggest you to do is read the history of Kelly Johnson of Lockheed Martin, which is called as the Skunk Works. What he did and how he kind of converted systems engineering into a profession, a much respectable profession. How he is revered as one of the most successful systems engineer. But at the end of the day, a systems engineer is supposed to be the glue between various teams. He is the one who combines all aspects of the systems engineering together. And to a large extent, a person who is trained in systems engineering, you have multiple diversification options. One could be into the financial, another could be in the technology management, a third one could be the pure technical. So this one will probably go into becoming the CTO of Chief Technological Officer or whatever. This could go into what you call as a CFO, the Chief Financial Officer, because after developing too many systems, you know how much it's going to cost and how the funds can be managed. The tech management, to a large extent, you can become what you call as a CTO, CMO. Then also another thing is you can this Chief Marketing Officer. Another example is also what you call as a CEO, how you could actually manage a technology company. You can see how Kelly Johnson was offered the job of CEO multiple times as well as, but he chose to remain as a CTO for quite a lot of time. With that, today we will conclude today's presentation. We will see in the next presentation on advancements on systems engineering. Thank you.